Hello everyone, welcome to Xenon Circuits crash course on basic electronics. The objective of the crash course is to aid the students preparing for campus placement drive in electronic based companies. The intended audience are pre-final and final year undergrad students specializing electrical and electronics engineering. Okay, so far we have covered 3 lectures in this series and this will be the 4th lecture of that series. In the 3 previous lectures, we had covered the basic concepts of finding equivalent resistance across series and parallel combinations of resistors, the concept of Wheatstone bridge or the balanced bridge, the concept of KCL, KVL, Ohm's law, and then naming the nodes in finding the R equivalent. And then we had introduced inductors and capacitors and how do they behave under DC steady state condition, along with how an ammeter behaves or an ideal ammeter behaves, right? So let's enter into the 4th lecture without further delay. Okay, so let's read the question. Find R equivalent across the nodes A and B at DC steady state condition assuming all components are ideal. So here the given constraints or the given hints is the first thing is DC steady state and the second hint is ideal component, right? And first let's look at the network provided in the question, and the elements that are used in this network are resistors and ammeters, right? So we have resistors and ammeter, and we know that resistors in DC steady state condition or in AC condition, it won't change much as it is frequency independent, right? And ammeter is also independent of frequency, but the other hint of ideal component will be working fine for ammeter because an ideal ammeter should have zero resistance as it has to measure the current. All the electrons should flow through it, right? Wherever it is getting connected, wherever we are connecting it, ideally the electrons should flow through that so that it will be reading the current through entering through it. That is the expectation of an ammeter. So in an ideal ammeter, the resistance has to be zero, or we can model it as a short circuit or an ideal wire, which is the wire with zero resistance, right? So now let's draw the circuit and simplify it and name the nodes. So this is node A. We have a 2 ohm resistor connected to it, and then we have an ammeter. As it's an ammeter, ideal ammeter, I am considering it as a short circuit. And then I have a 3 ohm which is connecting to the node B. Across node B there is one more resistor, 12 ohm of, let me erase this, another resistor of 12 ohm that is also connected to node B, and then this is also connected to the ammeter, and then there is a 10 ohm resistor connected between the either ends of an ammeter, 10 ohm, and then on top of that there is a 9 ohm resistor that is getting connected in series to a 3 ohm resistor which is also getting connected through the node B. So now if we see this, first let me name the nodes. This is also node B, this is also node B, right? And just by looking at this, I can say that these 3 ohm and 9 ohm are connected in series, so we can simplify that to 12 ohms, right? This will be reduced to 12 ohm, and then there is a short between this node and this node. Okay, let's name this node as C. This node is C, which means this is also C, this is also C. And if any element that is whose two terminals are connected to the same node, then the electron won't flow through that, right? I mean, the potential difference is literally zero. I mean, the resistor is connected through the two same nodes, which means potential difference across that is zero, which means there is no current flowing through it, and I can remove this resistor, right? So this is removed. So shall we redraw this circuit? Okay. If I redraw this circuit, the element 3 ohm resistor is connected to the node A, and then the node C is shorted. Then I have a 3 ohm resistor connected to node B. Apart from that, I have a 12 ohm resistor connected in parallel, and then there is a 12 ohm resistor connected in parallel. So now this circuit has become pretty simple to solve, right? So let's solve it. We can see that the three resistors, 3 ohm, 12 ohm and 12 ohm, are connected in parallel. Okay, for the sake of simplicity, let me just reduce these two resistors first, as they are of the same value. R equivalent will be R1 R2 by R1 plus R2, and as these are similar, this would be 12 by 2, right? 6 ohms. And then this is further connected to 3 ohm in parallel. So this will further simplify to 3 into 6 by 3 plus 6, as R equivalent is R1 R2 by R1 plus R2. So 3 into 6 by 9, and we'll be getting 2 ohms. And we can see that we have 3 ohm connected in series to 2 ohm across node A and B, right? So, and these two are connected in series, which implies that RAB is equal to 5 ohms. I hope most of you might have solved this problem, and you understood, if you had understood the previous concepts through the 3 lectures, this should be a pretty easy problem to solve. Okay, let's look another set of problem in the next lecture. Thank you.